Hello, my name is Professor Richard Magin. I'm a professor in the Department of Bioengineering at the University of Illinois in Chicago. And the title of my talk today is Fractional Calculus Models of Magnetic Resonance Phenomena, Relaxation and Diffusion. This is a talk organized as a part of the first online conference on nonlinear dynamics and complexity. And my thanks go to the conference organizers and particularly to Professor Dmitry Volchenkov of Texas Tech University. This talk is based on work that's been conducted by my colleagues and myself, some at the University of Illinois at Chicago in the Center for Magnetic Resonance Research, and other parts from around the country and around the world. So let's get right to it. Here's a summary of my talk. Well, it's a cartoon that I think encapsulates the summary. Gentlemen, this is just to give you an idea. Actually, there are lots of wires and things. So much for the light bulb. For this talk, the basic idea is that this work is in the field of magnetic resonance imaging, and it is to see if fractional calculus models of relaxation and diffusion can capture the complexity of brain tissue. The hope is that the adjustable order in fractional calculus, as opposed to the integer order operators, might give us some additional modeling and fitting parameters. If we can establish a connection between these parameters and the brain tissue complexity, then we'd also like to see if they are sensitive to the onset and progression of disease, specifically brain tumors. So that's the synopsis. Let's get to it. But before I talk about what I've done and what others have done with me, I want to try to put this into context and to make some connections between fractional calculus, magnetic resonance, relaxation, and diffusion. In a Venn diagram sense, the fields of magnetic resonance and fractional calculus and random processes in general overlap slightly. In particular, the overlap between magnetic resonance, the underlying nuclear magnetic resonance phenomena that's the basis for magnetic resonance imaging, is being applied and analyzed using fractional calculus. Fractional calculus, of course, is based upon a long history of mathematical advances that are now being connected with random statistical processes. In particular, the fractional relationships underlying the continuous time random walk and fractional motion models have been applied, and they'll be the focus of the techniques that I'll mention today. And the subspecialty where these applications are most relevant in imaging, for diagnostic purposes at least, is through the behavior of the water molecules in biological tissue as they move due to flow and due to diffusion, and the signals relax from initial perturbation to their returning to their equilibrium state. So let's look at some connections. We know that fractional calculus is applied widely in science and engineering. In particular, the fields of electrochemistry, viscoelasticity, and dielectrics are replete with fractional order generalizations. Here I'd like to talk about applying fractional calculus to magnetic resonance. And to be more specific, I'd like to talk about its applications in magnetic resonance imaging, not so much in nuclear magnetic resonance spectroscopy or in the allied field of electron spin resonance. Within MRI, the specialization that I will focus on concerns relaxation and diffusion. The classical model of relaxation yields exponential solutions, and those exponential solutions have time constants, the T1, T2 relaxation constants that affect image contrast and are used for diagnostic purposes. The fractional models are non-exponential or anomalous, as they're called. These models often use the Mittag-Leffler function, and you still gain relaxation times, T1 and T2, but you also have this adjustable order, the alpha, typically between 0 and 1 in the case of relaxation, gives you information about maybe the complexity of tissue. We'll talk more about that. Within diffusion, the classical models of diffusion in biological tissues, for example, follow a Gaussian process. The material is often, in the case of muscle and white matter in the brain, and cardiac muscle anisotropic. And so you need a tensor representation. But not all cases seem to follow these models. The non-Gaussian behavior occur in many tissues, and these models can be described using generalized versions of diffusion, and this involves a Riesz space derivative, and hence you then get the Mittag-Leffler function for the time behavior, and you get maybe a Riesz derivative putting its own influence on these functions. You still get diffusion coefficients, but now you have both time and space fractional orders to characterize the problem or the process. So first I'll talk about relaxation, then I'll talk about diffusion. It's this intersection of magnetic resonance, fractional calculus, and random processes. And I say I or we, gosh, I'm just awed to even be putting the names of the people in these circles, because they are certainly the pioneers in magnetic resonance, in random processes, and fractional calculus. It just shows you how the work that goes on in the past pushes forward into the future. Let's look at relaxation. The Bloch equations are the governing equations for magnetic resonance. It connects the net magnetization in material, the typical magnetic dipole moment per unit volume, and this magnetization in the case of MRI is just the magnetic moments of the hydrogen nuclei, the protons in water. So these slightly paramagnetic materials are manipulated through applied magnetic fields, the B of T here, and after these perturbations, the components, the X, the Y, and the Z components return to the equilibrium value with characteristic time constants, T1 and T2. The fields that are applied can be a static field, it can be a radio frequency field, it can be a field that's transiently applied, turned on and turned off, and all are typically used to collect images and to perturb the contrast in those images through the variations due to flow, diffusion, or relaxation. A simple example here shows you if you have a magnetic orientation around, say, the z-axis, the equilibrium value m0 will point along the z-axis. Applying a properly designed magnetic field perpendicular to this at the correct frequency, you can rotate this orientation of the m0, say, to along the y-axis, so-called 90-degree or pi over 2 pulse. And then at the end of that pulse, the magnetization just spirals right back in a time varying manner that's exponential. And so the fractional calculus version of this is to take this time varying magnetic field and generalize the time derivatives to fractional order time derivatives. We have 2 relaxation times, so we could certainly consider using 2 distinct versions of time fractional derivatives of different orders, alpha, say, for T2 and beta for T1. I showed earlier a little diagram that indicated that the fractional derivative sort of interpolated between all integer orders. Well, of course, like an adjustable wrench, they come in different sizes. So there are different kinds of fractional derivatives, and they vary in space and time, and they have different ranges and different properties. And what's worse, the alphas and betas that are applied to these particular derivatives and processes are not standardized. There are 24 letters in the Greek alphabet, but people seem to be comfortable using 2 or 3 of them, and they use them in a non-standard way. You always have to be very careful when you look at this field to make sure that it's clear which parameter is fractional parameter is affected by which property. Okay, so in looking at these equations, you can then solve them. And in the classical case here, in this example, we'll just assume that the z derivative is integer order of 1. You get a simple rising exponential. In the case of the x and y components, the relaxation decays not as an exponential, but as a stretched Mittag-Leffler function. So these little spiral diagrams here that Victor Vague and some of his colleagues worked out show how, as you change the order of the fractional derivative and you change the relaxation time, the spirals tighten or loosen and decay more or less quickly after perturbation. So you start out with a 90-degree pulse, and then the samples curve in different rates. So clearly the relaxation times have variations that are connected to the integer or fractional order of the process. And the applications of this in MRI uh, uh, allow you then to look at distributions of relaxation times. Speaking of time, I'm going to move on to talk about diffusion now because I wanted to try to highlight some of those contributions also. So in the case of diffusion, it is a little more complicated because one has a tissue like the brain, which has multiple compartments, multiple structures. And this structure then can be imaged in a virtual slice by slice basis with MRI. And what we're trying to do is paint a picture by varying the contrast in each pixel of each image or each slice in such a way that reflects some underlying subvoxel structure. And instead of trying to fit everything to every component in the cell, in the extracellular, in the vascular, extravascular, in the parenchyma and the extraparenchymal tissues, we'll just clump everything together in a simplified model, and then we'll take histology as a guide, but we'll use the model to formulate our fractional analysis. And then the fractional analysis will give us parameters that we'll paint onto the microstructure maps of the of each voxel in a particular slice. This is all pioneered by Danny Alexander and his group, and it's a well-established way of applying new models. The only different thing in this application is that we're using fractional models. Well, here's the Bloch equation we saw before. The first 3 terms here are the components that characterize relaxation. You can add a diffusion term and a flow term. And if you're clever in the way you apply gradients, you can get relaxation, you can get the image, you can get diffusion and flow, or diffusion or flow, depending on how you set the gradients up. The gradients that I speak of here are basically pulses of magnetic fields that are turned on and off in a synchronous way that allow the recorded signal to reflect the actual diffusion or the flow of the water that's contributing to the signal. Basically, you see you have pulses with an inverting pulses of gradients around a radio frequency pulse, and this time delay between these pulses gives this water an opportunity to either move or to diffuse. And depending on how you set the pulse up, you can then actually get a quantitative measurement of that diffusion coefficient or of the flow. The diffusion coefficient comes pretty straightforward in the XY component of the magnetization. And you see right away that you have now a sort of a generalized advection diffusion equation. You have a diffusion term, you have a relaxation term, you have a gradient driving force term that depends upon the applied gradient G, and you have the net magnetization that we're going to use to image. Surprisingly, the solution to this for simple materials is a simple exponential. And if you look at the signal that you record from a slice in the brain, you get signals that decay as an exponential, here plotted on a semi-log axis, as a function of the parameters that are established by the actual gradient pulse. These pulses here have a particular height, a particular width, and a particular separation. And this B value here is just the conjugate variable for the diffusion coefficient. So what we find is that we would expect the tissue signals to decay exponentially, which on a semi-log axis will be a straight line. And that's what you see for a simple liquid or for a simple homogeneous material. White matter and gray matter are not simple and they're not homogeneous, particularly white matter, which is anisotropic. So instead of having a straight line, you start seeing curved decay processes as a function of the, you think of the B as the strength of the diffusion perturbation. And so as B gets bigger, the effect of the diffusion is larger. And these decays characterize the actual tissue, because here this is pure exponential, this is somewhat exponential, and clearly the white matter is multi-exponential. So most people fit these things with stretched exponentials, multiple exponentials, multiple compartments, but we've been trying to use fractional calculus. In particular, we go back to the Bloch equation, and we'll look at the transverse component term, which is this advection diffusion equation. We'll ignore the relaxation or normalize for the relaxation. We'll fractionalize the diffusion process in terms of a space derivative. We'll fractionalize the magnetization time rate of change in terms of a time derivative. So we have a time derivative in alpha, a space derivative in beta, and we have gradients that we apply. And so in this model, we can then examine the diffusion and other parameters as they occur. One simple case that we published quite a while ago invoked a stretched exponential, where instead of just a fitting parameter beta just pulled out of the out of the air to support a model, this beta is exactly the order of the fractional space derivative. In the case, this particular case, we've just set the time derivative back to equal 1. And so in this case, you get this stretched exponential, which people had fit. And when you fit the data that we saw before in a slice of the brain, you get the diffusion coefficient, you get lower values here in the white matter than the gray matter, and you get higher values in the CSF right here. And that's as expected. The interesting things are the beta maps and the mu maps. The beta maps tell you something about the tissue homogeneity. The more homogeneous the tissue, the closer the beta is to 1. And then as the tissue becomes more heterogeneous and more complex, like the white matter in this region here, you have lower beta values. Similar phenomena occur with the mu. The mu parameter is needed to maintain the consistency in the units, and it has a unit itself of microns. So it's it talks about that it corresponds to the distance that the water is moving during these measurements. Another way to look at this diffusion model is to just generalize it in terms of both alpha and beta. And so this is the classical, in the fractional sense, continuous time random walk model of anomalous diffusion. And this model, if you take a Fourier transform, has a characteristic function, if you will, of a diffusion process that follows a stretched Mittag-Leffler in the parameter alpha and a space derivative involving the parameter beta. And this covers a multitude of underlying phenomena. The normal Gaussian diffusion ideally exists at this point of alpha equal 1 on the phase diagram of anomalous diffusion. Along this line to the origin, where 2 alpha over beta equals 1, you have a quasi normal diffusion situation. Everything up here in this quadrant, more or less, is normal diffusion. And when you are in these regions here of this phase diagram, you have processes that are that extend and grow faster than normal diffusion or slower than normal diffusion, subdiffusion, superdiffusion. This is characterized often by the mean squared displacement, and I'll talk, more about that in a little bit. So this model here is a generalization of the Bloch-Torrey equation, where we're including both fractional time, fractional space. This particular model was applied by Carson Ingo, a former student of mine, to look again at white matter, gray matter, and CSF of normal tissue. This is actually a rat brain, and he's looking at little regions here in the white matter and the gray matter, and these regions of the brain decay following characteristic curves as a function of this B value. The nice thing about MRI is that not only do you get numbers that correspond to particular decay curves, you can do it for every individual pixel in every slice, or depending on the slice thickness, every voxel. So you can make a picture. And in the picture, you have a dot, and each pixel component then has a particular value. So you get very nice contrast maps in terms of the alpha and beta parameter, in terms of the diffusion parameter, in terms of the time and space constants, and other parameters. Carson had some wonderful success applying an entropy model where he used normalized spectral entropy to combine all these factors into a very high contrast representation. These experiments took a long time. I mean, hours to do the data collection, and they were applied to a fixed tissue that had been removed from animals. So the question is, can you do this in a living animal? Well, with some constraints and some restrictions, this has been done successfully by Professor Tom Barrack in London, and he has fit the quasi-diffusion model right along this straight line in the phase diagram that I talked about. He's fit the data right along that line in such a way that he gets a stretched Mittag-Leffler where he only has two parameters, the regular diffusion coefficient that you'd get in an integer order diffusion model, and the homogeneity index. Remember, alpha is 1, it's exponential. Alpha is less than 1, it's not, it's anomalous. And so he's used these values to characterize the diffusion and the complexity of slices of normal brain tissues. And he's done this quite quickly in 228 seconds. So just in 3 to 4 minutes, you can actually collect all of this data. And what's more, he started to apply these results, and this has all been just recently published in NeuroImage, to some patients with neurodegenerative and brain diseases. So these models have the potential to interpolate between the integer order values, and these parameters appear to be sensitive to provide contrast that's new, different, and perhaps useful in diagnostic and treatment assessment purposes. In the last couple of minutes here, I'd like to talk about other variations on these models. Muge Carmen has done some work with a different version of this model, where the alphas and betas are independent, but likewise been able to fit them to patients with gliomas, and again to extract parameters that extend and add to the information that's gathered in conventional MRI. And we can think of this data then as a generalized phase diagram. Here's the phase diagram in the orange plane here that corresponds to the alpha beta map that we talked about before. And you can think of that as sort of the floor of a cube. And on this floor, you have superdiffusion and subdiffusion. And depending upon the alphas and betas, you have either Gaussian diffusion governed by the classical equation of diffusion, or fractional anomalous diffusion as governed by the continuous time random walk model. But you also have these individual cases, the so-called Levy process, which corresponds to moving right along the top line of this plane here, of this rectangle here, and the subordinated Brownian motion, which corresponds to moving along this line. So here you have cases where you have both space and time fractional order, here just time, here just space. And so you can pick the model that maybe is best tuned to the underlying pathology or the underlying structure. It could be trapping, it could be uh, 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 intravoxel incoherent motion. It could be other factors in tissue that come into play. There are many models that can be used. There's another whole set of fractional motion models where the diffusion is assumed to have some persistence or anti-persistence in it. And in these models, the actual diffusion process corresponds to parameters that fit a slightly complicated looking formula, mainly because, as I said, there are 24 Greek letters, but all of them are not used in a standard way. But the message is the same, that the fractional parameters give you new imaging biomarkers, if you will, that provide contrast, and that contrast can distinguish, in this case, between high and low grade tumors. So in this study, Muge and her colleagues have been able to show that you can follow the tumor and maybe determine the grade from the data, and the alternative being surgery or actually biopsy. Uh, this is quite significant. The point I'd like to make in finishing up here is that this model too isn't just the same as the phase diagram representation that we saw earlier for the case of anomalous diffusion for the Mittag-Leffler function. This is a slightly different function. In some ways, it's similar, but in other ways, it's different. You can calculate the mean squared displacement for this model of fractional motion, and this is all done in terms of the Hurst parameter, and this is based on some work by Fan and Go, which have used a Riemann-Liouville fractional integral. And the net result is that you have a Hurst exponent, and you have a beta, in this case beta equals 1, where beta here in this case corresponds to the time derivative. And now you have different combinations of the Gaussian process, the full fractional process, and the difference now has been made even more complicated by having a diffusion coefficient that's a function of time. It makes some sense that the diffusion that occurs in a heterogeneous complex material is going to vary with time, and that as it changes, as the water explores the intra and extracellular environments, and as those environments change, you would expect a diffusion to change. And so these equations now have parameters associated with the putative diffusion time behavior. You still get a time dependence of the mean square displacement. That's some power law. And it turns out, surprisingly to me at least, that this curve in this shape corresponds to a phase plane. It's not the phase plane here in the rectangle down here that we saw before. It's the back side of this cube. And so this fractional motion model corresponds to a sort of a z-axis that is a representation of the Hurst exponent. So the gamma here goes from +1 to -1, and you have sub and super diffusion, and you intersect the Mittag-Leffler representation of the alpha beta plane right down there. And this goes on and on. Matter of fact, almost any model you look at now, you can generalize the classic continuous time random walk model, where you have the alpha beta diagram, the mean square displacement that goes as time to the 2 beta over alpha. And here both beta and alpha run from 0 to 1. No, the beta runs 0 to 1, the alpha runs 0 to 2, sorry, or typically restricted 1 to 2. So you have a diffusion equation for anomalous diffusion, you have anomalous mean square displacement, and you have sub and super diffusion corresponding to this, call it the z equals 0 plane. The fractional motion model that we just looked at corresponds to the case where you have a different mean square displacement and you have a different governing equation. It's integer in time, it's fractional in space, and you have a power law representation for the diffusion coefficient. And there's a lot of statistical basis in terms of persistence and anti-persistence. So this model actually began with Mandelbrot. And it basically shows up as the back side, the back surface of this cube. And the process can go on. If you consider sort of the complementary model to this one, where you have a fractional time derivative and an integer space derivative, and a similar kind of version of the diffusion coefficient as a function of time, now you get a third representation of the mean square displacement. So you have 2 beta over alpha, 2 times 1 plus gamma over alpha, and you have t to the nu plus beta. And so it turns out these fractional power law models have been used to fit data, and it corresponds to the other face of this cube. So what we're trying to do is use the CTRW z equals 0 phase diagram as reference, and then we look above or below, in front or behind, by considering where the mean square displacements place the random motion and what the corresponding governing equations are. Okay, so just connect the dots here. Started out looking at magnetic resonance, applying fractional order model, looking at relaxation and diffusion. And I'm trying to look at how these processes can generate biomarkers that could be useful. Diffusion in almost all complex material is anomalous. The anomalous diffusion appears almost everywhere in biological tissues. And fractional calculus models, particularly models supplemented by time varying or space varying coefficients, are very versatile. And these models, I think, then give us hope for capturing unique perspectives on normal tissue growth and development and the consequences of disease. I'd like to acknowledge the collaborators, Muge Carmen, who I mentioned, Carson Ingo and Victor Veg, as well as Tom Barrick, and then others, Amin Karani, Matt Hall, Huazhu Zhang, Guanyu Dong, and Zhaihong Zhou Zhao, who have been working in this field and who, with their students, have contributed a lot to the material that I've presented. I'd like to finish up just by pointing out that this intersection between modeling and medicine and mathematics is very interesting. And in the case of MRI, it's important to have a good model and to use both the physical systems and the mathematical methods to extend that model as much as possible. So I'll end here, and then we can go online and talk, and I'll be happy to try to answer any questions. But thank you for your attention. Some of this work has been published, some of it is coming out soon. So feel free to contact me if you have any questions.